there's three measures of variability: the range, the variance, and the standard deviation. So the range is the one we're going to start out with first, and this is the easiest to do. So the range is just the maximum value minus the minimum value. Okay, so you take the max and then you subtract the min. Pretty easy. That's the range. Okay, so check this out. Look at these three data sets. So here's the first data set. And when we look at this first data set, we've got 10, 20, 30, 40, 50. They're all equally spaced, okay? 10, 20, 30, 40, 50. Piece of cake. What is the mean? What's the average? Well, it's 30. What's the median? The middle number, that's 32, or 30 as well. What is the range? The range is going to be 50 minus 10 for a grand total of 40. So this is our first data set, equally spaced, 10, 20, 30, 40, 50, very well behaved. Very nice. Let's go to the second data set. So the second data set are these values: 10, 29, 30, 31, and 50. And you can see this is a different data set. The numbers are sort of clumped in the center. Well, let's find out what the mean is. Let's find a couple measures of center. So the mean is 30. Oh, how about that? The median is also 30. And the range, 50 minus 10, well, that's 40 as well. So we've done three sort of looking at these two data sets three different ways: the mean, the median, and the range. And according to the mean, median, and range, these data sets are identical. They're exactly the same. There's no difference between them. But looking at the data sets, you can see that there's a difference. The green data set are equally spaced, where the blue data set is sort of clumpy in the middle and has these little points that are far out on the edges, okay? Let's do one more data set. So if we look at one more data set, here is 28, 29, 30, 31, 32, okay? The mean is 30, same as the other two. The median is 30, same as the other two. The only thing that's different about this one is the range. The range is 4, and so that's a little bit different. But so the mean and the median, even though they're good measures of central tendency, they don't tell us really how much variation there is in a data set. And even the range doesn't quite do a good job. So what we'd like to do is this idea, and I'll show this to you graphically. What we'd like to do is we'd like to take the mean, the number in the middle, and then for each point, we want to find out how far away are you from the mean. How far is each point away from the mean? So 10 would be 20 away from the mean, 20 would be 10 away, and 20 away. And what we'd like to do is find out what's the average distance from the mean. If you were to first find the mean of the data set, what is the average distance? If you took every point and found its difference from the mean and then added them all up, divided by how many there are, that'd give you a good measurement, like the average deviation. We could do the same thing here. So the difference here would be 20, but then this distance would only be 1. And this distance would only be 1. This distance would still be 20. So you'd probably have a lower average deviation, right? That's the idea. That's what we want to do. We want to measure what's the average deviation. What's the average spread outness of our data set? What's the average deviation from the mean? And so that's what we're going to do. So here's going back to our cat data. Here's our 5 cats and their weight, okay? And we're going to find the mean of the 5 cats. So there you go. There it is, 8.02, done. Okay, now let's find the difference from the mean. So we take each point, 6.8, and we subtract the mean. So 6.8 is 1.22 below the mean. Below the mean, right? That's what the negative means, okay? So this value is below the mean. 8.2, on the other hand, is above the mean. 0.18 above the mean. 0.75 is below the mean. 0.52 units below the mean. 9.4 is above the mean, and 8.2 is above the mean. So all we have to do now that we've got the deviation from the mean is let's add them all up and divide by how many there are. Piece of cake, right? We got this. This is an average, piece of cake. So we add these up and we get 0. What? 0? I can't divide 0 by anything. What's the deal? Why do we get 0? Well, you get 0 because half of the numbers are above the mean and the other half are below the mean. And this will always happen. Every time you try to do this, no matter what your data set looks like, when you take the mean, half the numbers are going to be above it, half the numbers are going to be below it. And when you add them all up, the positives are all going to cancel with the negatives, and you're going to get boop, 0, zipka, nothing, done. Oh, man. Here's the 0. We get 0. So I call this the 0 problem, right? Because we keep getting zeros. And so what we're going to do, follow me on this, we're going to apply a mathematical trick in order to get around this problem of the zeros, okay? Here's the mathematical trick. We're going to square the difference from the mean. Because, squaring things make them positive, right? And so if you take this difference from the mean and you square it, ta-da, positive number. Square this difference from the mean, square this difference from the mean, square this difference from the mean, square it. And now add up the squares of the difference from the mean. This is the sum of the squares. Oh, I've seen that before, SS. This is the sum of the squares of the difference from the mean. That's the sum of the squares. Fantastic. We've gotten around the 0 problem. Now we can add them up and divide by how many there are. And that's exactly what we're going to do. And we're going to call that the variance. And so the variance is the sum of the squares of the difference from the mean. That's what this thing is. And if you're doing this for a population, you divide by the number of items in your sample set. Okay, so we're going to divide by 5. And here is the variance if our data set was a population. Our data set's not a population. It's a sample, right? It's a sample of 5 cats. And so when you calculate the variance for a sample, you do the exact same calculation, but you divide by n minus 1. You take the number of items and subtract 1. Some students have asked, why is it? Why do you subtract 1? Why not subtract 2 or 3 or 4? And the best that I can come up with is that this is just what they decided to do a long time ago, and it works, and everybody's agreed to it. Okay? It's one of those things where, like, I'm sure there's a mathematical explanation for this, but it's probably kind of on thin ice. And so let's just go with this. Okay? So most of the time, 90% of the things you do in this class are going to be with samples. So you want to do this n minus 1. And by the way, boom, here it is. There's your variation. That is the average deviation from the mean of every point with our squared trick built in, okay? That squared trick built in, though, is causing a trouble with the calculations. Like, we did something, right? Like, you can't just go around squaring every number. At some point, you have to undo that squaring. And so if you take these numbers and you square root them, that is what we call, that undoes our squaring trick. That is what we call the standard deviation. And think of this as like the average deviation. Standard deviation is kind of like average deviation. It's not really quite an average because we had to do the squaring and the unsquaring, but this is the standard deviation for a sample. And again, it's divided by n minus 1. This is the standard deviation for a population, again, divided by n, okay? And this really is the number that you are going to see most frequently. Standard deviation, not variance, and for a sample, not for a population. But we have to show you both, right? We have to show you how to do this both ways, okay? And there it is. That is the standard deviation. That is the magic number that we're looking for. So if you have a large standard deviation, if you have a large number for a standard deviation, that means your data is spread out all over the place, okay? If you have a small number for your standard deviation or average deviation, that means your data is clumpy. Your data is kind of clumped around 1 or 2 points, okay? And so that's how we use measurements of standard deviation. So as an example, we're going to take a look at this example. We've got employees that are working and they're being trained. Okay, one group is using training method number one. Let's say this is a face-to-face group. They all come in and they do this task face-to-face. They learn, be trained on it, and then they're timed to see how long it takes them to complete a task. And here it is. Boom, 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 boom. Person number one does it in 56 minutes. Person number two in 75 minutes, 48, 63, 59. And they have an average of 60.2 minutes to complete the task after being trained by training method number one. Then you have another group of people that come in and get trained with training method number two. And these are their times for completing the exact same task. And if you go and find the average, you find out that the averages are exactly the same. So what training method is better? Right now, when we look at the means, it's a tie. They both have an average of 60.2 minutes. Training method number one has an average of 60.2. Training method number two has an average of 60.2. So let's look at the standard deviation. So what we're going to do is we're going to take training method number one. We're going to find the mean. We know it's 60.2. We calculate that already. Now we're going to find each point's difference from the mean. Then we're going to square that difference from the mean and then add them all up. So the variance is going to equal 394.8 divided by 5 minus 1. Remember, this is a sample of employees, and so we're using n minus 1. So whatever you get for this, that is the variance, okay? The standard deviation is going to be the square root of that number. And that's really what we're looking for. Variance is nice, but we really want that standard deviation. So we're going to square root that number, and we're going to get a value. We're going to take that value, we're going to compare it to the next group, okay? And so, by the way, here is the next group. So what we do with this group is, again, we measure all of their times. Boop, 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 boop. We find the mean. We find the difference from the mean, the deviation from the mean. We square the deviation from the mean, and we get a total. And now to find the variance, we're going to take that total, 44.8, and we're going to divide it by 5 minus 1. That will give us the variance. Okay. Once we have the variance, to find the standard deviation, we just square root that number. Whatever that number is, take the square root of it. Because remember, we had to undo the square trick. The reason we do the square root is because earlier we squared. So somewhere we got to unsquare, which is square rooting, in order to make everything balance out correctly. Okay. So here are the numbers. Here's the variance. And here's the standard deviation. So group number one had a standard deviation of 9.93. Group number two had a standard deviation of 3.35. So how do you interpret this? Group number two had a lower standard deviation, which means they were more consistent. Group number two was more consistent in the amount of time it took them to accomplish the task, okay? If you were to graph it, and you probably could look at the graph. I don't think I've actually graphed this, but group number two, all their times were probably something like this, okay? Group number one probably had a lot more deviation in between the times. Some did it really, really slow. Some did it really, really fast. They were inconsistent. There was a lot of deviation, numbers all over the place, right? Where group number two was much more consistent. It was a tighter group of numbers, less deviation, more consistent, okay? Now, when you're doing an example like this, and you're talking about workers and accomplishing a task, sometimes you want a low standard deviation, especially if you're taking a look at things like manufacturing. So if you're manufacturing bolts and you want to make sure that the bolts are all the same length and have the same size and the same mass, quality control, you want a very small standard deviation. You don't want any deviation in those, right? If you buy anything in think about buying a pair of shoes, right? So you have a shoe size, and have you ever gone and like bought one pair of shoes and they fit just right, and then you buy another pair of shoes, they're the same size, but they fit differently? Quality control. There's a large standard deviation in between those two shoes, even though they're the same size, or they're supposed to be, right? So sometimes you want a small standard deviation for quality control. Other times you would like to have a large standard deviation. And what a large standard deviation will do is it'll help tease apart those clumps. For example, let's say that you are applying to an Ivy League college, okay? And most students that apply to Ivy League colleges are the top of their class. They're valedictorians. They've got 4.0 GPAs, if not higher. And so if you're working at the admissions office of this high performance university, and every single applicant that you get is a 4.0, how do you tease them apart? You want to give them some type of an assessment that has a large standard deviation. So that way you can take that clump of data and kind of spread it out and see really who is the best of the 4.0s and maybe who's not the best of the 4.0s, okay? And so depending on the situation, you may want a large standard deviation or a small standard deviation. It's depending on the situation, okay? So that is the end of, it's not? Oh, yeah, the last thing is the technology. So I was just going to jump right into the spreadsheet if it's all the same to you. Here are the formulas that we're going to use in the spreadsheet that we'll get to in about 30 seconds. VAR is the variance of a sample. VARP, VARP, is the variance of a population. Notice the P, right? VARP, population, okay? Same thing with standard deviation. STDEV is the formula for a standard deviation of a sample, the one you're going to be using most often. And then STDEVP is the standard deviation of a population, the one you may not be using so often, okay? And so basically you're going to copy and paste your data into a spreadsheet, use these formulas, and it will calculate all of this for you. But before you do that, let's show you how to do this by hand. That's right. I want you to do this by hand first, or not by hand, but do this the long way first without formulas. And then we'll let you use the formulas and we'll compare the two and see how it goes. Okay. So here it is. This is the 3.2 Google Sheet spreadsheet, and we're going to walk you through this really quick. And so what we have here are, what do we got? 25 scores, right? And again, this is a random situation. So if I click off on an empty cell and push delete on my keyboard, all those numbers randomize, okay? So the first thing we're going to do is we are going to, well, let's give this a name. What do you want to call this data set? I'm open to single syllable names. Drop one in the chat. We're going to name this range. What do you want to name this range? I need a single syllable name. Ted. Hello, Ted. Ted, meet everybody. Everybody meet Ted. Okay, this is our data set. Everybody say hi to Ted. Here we go. The first thing we're going to do is we're going to find the mean of Ted. So I'm going to zoom in a little bit so you can see the formulas that I'm going to write down. Here we go. Okay, so mean is AVERAGE, the average. And we're just going to say the average of Ted, right? We don't have to select the cells or anything like that because we know Ted is that data set. Boom, there we go. There's the average of Ted. Now let's find the count of Ted. How many items equals COUNT? How many items are in the data set Ted? And it says 25. And you can see if I go in here and delete a couple of these items, the mean automatically changes and the count automatically changes. See, there it is. Boom, 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 boom. So we've built this dynamically so that way, as our data set changes, these values change automatically. Wonderful. Now we've got the mean, right? We need to take each point and find its difference from the mean. How far away above or below the mean is each data point? Okay, so let's take a look at that. So we're going to go back up here and we're going to say equals this data point, that's the first one, minus the mean, that cell right there. Okay, now we are going to fill this down. And when we fill it down, we want the orange rectangle to go from A2 to A3 to A4 to A5. We want that one to move. We do not want the purple rectangle to move. We don't want this rectangle right here, the 80.9, to move down to 29, 30, 31, 32, because there's no data down there. We want to keep it right at 28. So to keep it right at 28, we're going to put dollar signs in front of the A and a dollar sign in front of the 28. The dollar sign in front of the A freezes the data point, freezes column A, and the dollar sign on the 28 freezes the row 28. So we'll hit enter. And now when we do our fill down, we'll fill this all the way down. There we go. If you click on this cell, you'll see that the orange rectangle moves to 23 and the purple rectangle stays on the mean. The next cell does the same thing. Orange rectangle moves down to 24. The purple rectangle stays on 28, which is exactly what we wanted it to do. Okay, fantastic. So now we have the difference from the mean. And just for fun, just to show you right here, I'm going to add these all up. All right, check this out. Equals sum of all these differences from the mean. And there you go. What are you going to get? You're going to get 0. You are going to get 0. And it doesn't matter how many times, it doesn't matter how many times you refresh your data, that sum will always be 0 because half the numbers are above and half the numbers are below. Half the numbers are positive, half of them are negative. They're all going to cancel and give you 0. That's what happens when I add them all up. And this is a problem. So to fix this problem, we are going to play a little trick and square every number. We're going to raise every number to the second power. There we go. And now I'm going to fill this down. And then I'm going to add these up. There we go. Right there it is. That is the sum of the difference from the mean squared. It's the sum of all of those difference from the mean squared. Okay, so there's our number. Now, all we have to do is divide this number by the count, and we'll have the variance for the population. If we divide this number by the count minus 1, we'll have the variance for the sample. Okay, and we're going to do both. So we've got those calculated up here at the very top. So for the variance of the population right here, the variance of the population, I'm going to say equals the sum of the squares divided by the count. So I clicked on the sum of the squares right here, and I divided it by the count of the number of data points that we have. Don't type 25 in there, because if you delete a couple data points, leaving that 25 in there, it's always going to stay 25. And if you reduce the data points down to 24 and you still have 25 in your formula, that's going to be a problem. So you want to make sure that you click on the cell address so this remains dynamic, right? We don't want static numbers in our formulas. That's why I'm using all of these cell values. And right there is the variance for the population, okay? Now, all we have to do is square root this number, and we got the standard deviation. So we're going to say square root that 24, which now is a 31 because all the numbers changed every time I hit enter. And here we go. Boop, boop, boop. See, look at all that crazy changing happening in that number set. Look at that. Okay, so here's our population variance. Here's our population standard deviation, all done by hand. Okay, now let's do the same thing, but for a sample. And the only difference is, instead of dividing by 25, we're going to divide by 24. Okay, we got to subtract 1 from it. So here we go. We're going to click on the cell. We're going to say equals. We're going to select the sum of the squares, and we're going to divide it by, and I'm going to use parentheses here. I'm going to click this number minus 1. You have to use parentheses, otherwise it will divide the two numbers and subtract 1 from that quotient rather than dividing by 24, and you'll get the wrong answer. So we'll do it this way. There is the variance for our sample right there. And now we're going to find the standard deviation by simply taking the square root of that variance, undoing that square trick that we did a while ago. So SQRT of this number. And there we go. Here is the population of a population variance, population standard deviation. Here is a sample variance and a sample standard deviation. And again, this is dynamic. So as my data set changes, as all my test scores re-randomize, all of the calculations I've done also re-randomize. Okay. So now we've shown you how to do this by hand. Let's use the formulas. Ready? Here we go. Don't blink. You're going to miss this. Equals What is the variance population or variance formula for a population? VARP. VARP of who? VARP of TED. And there is the population variance. Done. Did you blink? Did you miss it? There it is. And notice it's the same as the number we did by hand. See that? 42.08, 42.08. So that's VARP of TED. Let's do STDEVP of TED. Whoops, I got to put an equals in front of that. Sorry. Oop, there we go. Here's the variance of TED. Here's the standard deviation of TED. And they're the same numbers as what we calculated by hand. Okay, let's do sample variance. So remember the formula for sample variance? VAR. What's VAR of TED? 48.2. What is the standard deviation of TED? Equals STDEV of TED. There you go. And notice that these four boxes, the four yellow highlighted boxes that we did painstakingly by hand, step by step by step, calculate this, do that, square that, divide by this, all these steps you got to do. They match exactly with the four boxes that we used the formulas for. And you can re-randomize all you want, and those four boxes should always match if you've built it by hand correctly. Okay. If you've got an error, if, for example, our population box here that we did by hand, step by step, and our population box for our formulas, if those don't match, you've done something wrong, either in your formula or in your step by step. So go back and double check it. Okay. So what I'm looking for when I go through this are, do these boxes match? Do your step by step calculations match? Okay. And don't copy the formulas from here and paste them into here and pretend that they match, because I'm going to go and look at your raw data, and I'm going to look at your sum and your mean and your count, and I'll know if you did that. So don't do it. Just don't build it one time by step, right? Doing all of this tedious work. And then from then on, you'll be able to use VARP and VAR and STDEVP and STDEV.